Today we will use parametric equations to explore circular motion. We'll start with an example. Suppose a pebble lodges in a wheel that has radius 12 inches. The wheel rotates at a rate of 20 times per minute. First question I have for you is, if the wheel rotates 20 times per minute, how long does it take to complete one revolution? Well, keep in mind there are 60 seconds in a minute, and we've got 20 times per minute, so it takes it 3 seconds. That'll be important later on. We are going to write a pair of parametric equations to describe the path of the pedal, and we're going to assume that this wheel is rotating clockwise. So this is a wheel with a radius of 12 inches, and there's the pebble that got lodged in the wheel. And we're going to start considering the vertical component. How far above the ground is this pebble at any given time? Well, it's starting right there at the bottom. So that pebble's on the ground. Now we start the timer. This wheel's turning clockwise, and the pebble is going with it because it's lodged in the tire. So after some period of time, that pebble is halfway up as far as its vertical distance is concerned. And if the radius is 12 inches, it's 12 inches above the ground. Now the wheel continues rotating, the pebble goes with it, and after an equivalent period of time, the pebble's now at the top, and that's going to be 24 inches above the ground. And the pebble continues its journey around the circle. Now it's only 12 inches above the ground, and after one complete revolution, the pebble's back where it started on the ground. Now, how long did it take to make that complete revolution? Well, as we said a minute ago, it took it 3 seconds. So the period of this curve is 3. And now we're going to write the equation. So we have an amplitude of 12, a vertical shift up of 12 units as well. This is a cosine curve starting at the bottom, so that makes it a negative cosine curve. So we have the vertical shift of 12. Because it's a negative cosine curve, I have the minus 12 cosine, and then it's 2 pi divided by the period of 3 times t. So that describes the path of this pebble vertically, where its position is at any given time in seconds after it starts spinning. All right, well, let's take a look now at the horizontal movement. Now there are 2 parts to this movement. First of all, the pebble is just moving around the circle the same way it was a moment ago, and its position relative to an axis that runs right through the axle of this wheel can be measured. When it's to the left of where it is right now, I'll call that negative, because it's behind the center of the wheel. And when it's to the right of that point, I'll call it positive because it's to the right of the center of the wheel. And if it's right in line with the center of the wheel, we'll say it's 0 units left or right of center. But the wheel is also traveling forward. We know that it's traveling forward because the wheel is rotating on the ground. So we need both parts. All right, so as I start, the pebble's on the ground and it's right below the axle. So it's 0 units from that axis. The wheel's turning clockwise, and so here we are, a quarter of the way around the circle, and the pebble is now 12 inches to the left of the axis. That's negative 12. We continue our trip around the circle. Here's that pebble again at the top. Now it's right in line with the axis again. It's above the axle, but that doesn't matter because I'm interested in horizontal movement, not vertical. And we keep turning. And here it is to the right of the axle, 12 inches, and that's positive. And then back to the bottom where it's in line with the axle again. So again, it took 3 seconds for a complete revolution, and this is now a sine curve. It's starting in the middle. It's going down though, so it's a negative sine curve. It has the same period it had before. So I've got that part to consider, plus I've got the fact that this thing is moving forward. Well, how far does it go? It's traveling basically the circumference of this circle, but In 1 second, it's only gone a third of the circumference. Well, the circumference is pi times the diameter, so that would be 24 pi. If I've only gone a third of it, I'm going to have gone 8 pi times the time. So that's the forward movement of the bicycle or the wagon or whatever this wheel is on. And then I need the part for just the oscillating left-right movement because of the turning of the wheel. And so there is your pair of parametric equations. I chose to write y first. Doesn't matter, I just need both of them because parametric equations always come in pairs. All right, let's take a look at another example. So in this one, I've got a bicycle traveling forward, which I'm saying is to my right, at a rate of 15 feet per second. This is sort of a leisurely bicycle ride. The pedal makes a full circle every second. The pedal radius is 8 inches, and its axle is 11 inches above the pavement. We are going to write a pair of parametric equations to express the movement of a spot on the side of the pedal. So this is the pedal now, not the wheel. Given that when we begin timing, the spot is at its furthest point forward, as far to the right as we can get. So we're going to start with the vertical motion. So it is now furthest point to the right means it is above the ground, equivalent to however far the axle is, and that's 11 inches. So it's 11 inches up. And then as the bicycle moves to the right, the pedal goes down, and when it's at the bottom, it's 8 inches down from its axle. It's still 3 inches above the ground though, and it continues going around until again it's level back to the 11 inches, and then it continues going up further until it's 19 inches above the axle. And it just keeps rotating around a circle that way. So if I'm interested in the vertical motion, well, I've got a vertical shift of 11 inches, that's the axle. My amplitude is 8 inches because it travels up and down 8 inches above and below that middle position. And then I just need to consider the period. So here's a picture of what it would look like. Starts in the middle, goes down, goes back up. The 11 was because of the vertical shift. The 8 was the amplitude. You can see in the picture it's going down first, so it's a negative sign. And then because it makes a full circle every second, 2 pi divided by 1 gives you the number in front of t. All right, now let's look at the horizontal movement. And don't forget, this bicycle's moving forward, so there's 2 components to it. Going that way. It's going at a rate of 15 feet per second. Well, one thing to consider is that I've measured the radius in inches. I've measured the distance in feet. I need to convert that to inches. Here's what it's going to look like. It's starting as far to the right as it goes, it said. So that's a positive value. And then it's going to go down to where it's right below the axle, where it crosses the axis at 0. And then it's going to go to back, which means a negative value, again 8 inches, and then it continues around the circle. So 15 feet is 180 inches. I got that by multiplying 15 by 12. So there's my equation. It's going 180 times t, inches to the right, plus, and now you've got the backward-forward movement of the pedal itself. Radius of 8, period, we've got the 2 pi divided by 1, gives us the value in front of t. So there's 2 examples for you. And now it's time for you to give this a try. If you go to ClassKick, there is a lesson. It says Math 603, The Bicycle Problem. Some of you had a chance to look at this problem last week on Thursday. Many of you, if not most of you, did not. Either way, I'd like you to go and do some bicycle practice problems now. And that's it. So have a lovely afternoon, and I will see you soon.